class, this is our review video about how to take a Lewis dot structure and turn it into a valence bond diagram. Now the difference between those is that a Lewis dot is going to look very flat. Okay, and it only takes some things into consideration. What we're going to do is we are going to take hybridization and 3D structure, and we're going to turn that into a valence bond diagram that looks something more like this. Okay, and there are electrons in each one of those. Alright, so I'd like to start by kind of reviewing the steps of making a valence bond diagram. Alright, these are the rules that we went over in class, but I just kind of want to go over each one again and talk about where you're getting this information. You're always going to start by drawing a Lewis structure. We're going to do that always the way we would do it in class, where we always start with a central atom. You're going to count valence electrons. And then you're going to try and make single bonds. Make sure everything has an octet. Okay, so the same rules we always used for the Lewis structure. The next thing that you're going to do is you're going to use Vesper theory to predict the electron group geometry around each central atom. If there's more than one central atom, you're going to do this one at a time, one for each central atom. So you do it for one central atom and then the other one. And when you predict the electron group geometry, things you're taking into consideration is how many bonding groups there are around the central atom. You're going to take into consideration how many lone groups there are around the central atom. And if you are having trouble with this, or this seems unfamiliar to you, we're going to look at chapter 9 in the Tro book, or you would use your lab 13, experiment 13 charts to decide what the electron group geometry is. Kind of familiar words should be things like tetrahedral, or linear, or like trigonal, planar, things like that. So those are the kinds of words we're looking for. We're basically looking for a 3D structure around that central atom. The next one is predicting the hybridization scheme that matches the electron group geometry. Now this thing, ED, that's electron domains. And it basically just means electron groups. And what's reminding you to do there is to count the number of electron groups around the central atom and use that to decide what kind of hybridization the central atom is going to do. So I'm just going to use this example down here. You might have seen me do this one in class, but we'll use it again here. My central atom is carbon. And around the central atom, there is 1, 2, 3 electron groups. So 3 electron groups, 3 electron domains means the same thing. And when we have 3 electron domains, the hybridization is sp2 hybridization. There's a chart in your lab 13, and there's also a chart in chapter 10 now in your Tro book that would help you find out the hybridization once you know how many electron groups are around that central atom. The next thing that we're going to do is sketch the hybridized orbitals around the center atoms. When you do this, you're going to try and take into consideration their 3D shape. So when we say something has like sp2 hybridization, and up here we had decided that it was trigonal planar, we're going to try and draw those sp2 hybridized orbitals in a trigonal planar way. Next, we would sketch the atomic orbitals on the terminal atoms. Remember, terminal atoms mean the outside of the molecule. And we are going to show the overlap of appropriate orbitals and add electrons. So that basically means we just need to make bonds by looking at the atomic orbitals that those atoms the atomic and hybridized orbitals that those atoms would use to bond. And I added this one. If you didn't see me do this one in class, I made this an extra step. If there's a pi bond needed, and we'll talk about how we would know if it was needed, we're going to draw the overlap of unhybridized orbitals. So we'll do that if we need to do it. And the last one is label the bonds. When we label bonds, we always label it with the type. So our choices there are sigma or pi. And then we put a colon, and then we put the atom and which orbital it used. Then we use a hyphen, and we do another atom, which with orbital it used. Like that. Okay, so let's do these steps for this actual molecule here on the next slide. Okay. So you might, again, have seen me do this one in class, but the molecule is CH2O, and we're going to go down this list. The Lewis dot structure has carbon as the central atom. The hydrogens are going to be on one side, or different sides, and the oxygen's going to be on the other. If I'm counting up valence electrons, carbon has 4, then each hydrogen has 1, and oxygen has 6, so that is 12 total. And I'm going to put those electrons in by making single bonds first, and then, so I've only used 6, I'm going to put the other ones around, and what I notice is I do not have enough electrons to put out here. So what that means is that I need to use a double bond. I'm going to take electrons from something that has a lone pair, maybe like this carbon here, and I'm going to make them a part of that double bond there. I'm going to kind of erase, I got to erase this a little bit. Okay, so I've made my double bond between the carbon and the oxygen. So I've done this part. The next part is use Vesper theory to predict the electron group geometry around the central atom. I can see that there are 3 groups of electrons around my central atom. So there's 1, 2, 3 groups. All of them are bonding. And so 3 groups around the central atom would spread out in a trigonal planar way. Okay, so I've done that. We decided that it was trigonal planar. The next one is predict the hybridization scheme that matches that electron group geometry. Anything that is trigonal planar has 3 electron groups, or 3 electron domains, and 3 electron domains is going to be sp2 hybridization. If you haven't seen the chart, the way that it goes is like this: the number of electron groups and hybridization. The lowest amount of electron groups you can have around a central atom is 2, then 3, then 4, 5, 6, and the hybridization is sp, sp2, sp3, sp3d, and sp3d2. Now there are technically, theoretically, more lower than here, but 6 electron groups around the central atom would be 12 electrons, and that's really the most that we have seen atoms do. So we've decided that it's sp2 hybridization. The next thing is sketch the hybridized orbitals around the center atoms. And like I said before, we are going to try and sketch those sp2 hybridized orbitals around the central atom, and we know that they are going to be in a planar shape. sp2 is not an s orbital. It's not a p orbital. It's an sp2 orbital, which has 1 lobe. Something like that. So that's one of them. There are going to be 3 of those around the central atom. So I'm going to draw my central atom here, and I'm going to draw the hybridized orbitals around it. I'm going to do them in maybe some different colors here. So that is one of the orbitals. This is another of its orbitals, and I'll do this one. So I just drew 3 sp2 hybridized orbitals around the carbon atom, which is my central atom. So I've done that. Next is sketch the atomic orbitals on the terminal atoms of the molecule. Our terminal atoms are hydrogen, hydrogen, and oxygen. So when I draw the atomic orbitals around the hydrogens and the oxygens, I'm drawing the atomic orbitals for which block they are in on the periodic table. Hydrogen is in the s block, so I'm going to draw s orbitals for it to hybridize with, or to bond with, sorry, not hybridize with, but bond with. And so here's a hydrogen, and I'm going to draw the electrons in their bond there. Now I could have chosen any 2 of these 3 bonds to put the hydrogen in. So I could have put the hydrogen on the right side instead of the left side. It would make no difference. But I've left some room open for this left side so I can do my oxygen. Oxygen, I'll just make green here. Okay, so I'm going to draw an oxygen. Oxygen's in the p block, so it's going to bond with its p orbitals. So that's why I'm drawing 2 lobes, because orbitals have 2 lobes. And I'm going to draw some electrons in there. Okay. Oh. I'm feeling red there. Okay. Number 6, it says, if a pi bond is needed, draw the overlap of unhybridized orbitals. To know if a pi bond is needed, you're looking at your Lewis dot structure, and if there is a double bond, in a double bond, the first bond is a sigma bond, the second bond is a pi bond. And so we have done this one by making an overlap there, but we still need to explain this pi bond. To explain the pi bond, we need to draw overlap of unhybridized orbitals. A pi bond happens when unhybridized p orbitals can overlap with each other. The only way that can happen is if there is an unhybridized p orbital. So when we look at our hybridization scheme, it looks like we used 2 out of the 3 available p orbitals, so that means that there was a p left over. 1 p orbital was left over. It was unhybridized. So I can draw that around my carbon atom, and when I draw it, I'm going to draw it perpendicular to my hybridized orbitals. Remember, p orbitals have 2 lobes. I'm going to do the same thing for my oxygen. Oxygen's in the p block, and all of its p orbitals are unhybridized. It has 3 p orbitals. It's already used 1, which is the green, and now I've drawn another one, which is the blue. So these hybridized, unhybridized p orbitals can overlap. I'm just going to draw those in like this. And I know that there are 2 lobes, a top lobe and a bottom lobe here, but they are 1 bond. Okay, now I didn't really get to draw my electrons in here, but I'd like to draw 1 in the top and 1 in the bottom, because that reminds me that there are 2 electrons in that bond, and that the electrons like to spread out. Okay, we have one thing left to do, and that is labeling the bonds. I'm going to maybe label them in black, just so that they are different than the other colors. These over here, they are sigma bonds, which are single bonds made from hydrogens, s orbitals overlapping with carbon's sp2 orbitals. And we could have switched these, so you could do the carbon sp2 first if you wanted, but it doesn't really make any difference. You're just saying what overlap we had. this bond here is also a sigma bond, and it's made from carbon's sp2 overlapping with oxygen's p orbital. The p orbital is this green one that I just made black. Okay, we have one more bond to go. We have this pi bond we made, and it's made from carbon's unhybridized p overlapping with oxygen's unhybridized p. Now I want to show you the prettier version of this, the one that your book made for this molecule. But before we do that, I want you to kind of reflect on what we did here. I know that we did a lot of work, and it's easy to kind of get caught up in the steps and wonder if you did all the things that you were supposed to do. One thing that I always like to do is I like to look back at my Lewis dot structure, and I just want to make sure that I explained all the things, okay? So when I say that, I mean, did I explain that there's a carbon-hydrogen bond, another carbon-hydrogen bond? Did I explain that there is a sigma bond here? And did I explain that there was a pi bond there? And if I've explained all the bonds, then I've made a good valence bond structure. Okay, so this is the obviously prettier version of this molecule that our book has done for us. It is taking the Lewis structure and it's making it into a valence bond diagram, a valence bond model. You can see the way that they put the electrons in there is really nice. It's got labels. The pi bond obviously looks better than my overlap, but all the things are there, just like we did it. Okay. The next thing I want to do is I want to do it for a different molecule, one that we haven't done before. This is CH3CHO, and the first thing we're going to do, so I just have the list of things to do here. The first thing to do is draw the Lewis structure. When you see a structure like this one here, the way that the formula is written has a lot to do with how you're going to do your Lewis structure. In general, you're going to use the carbons as kind of like a backbone. And when I look at these, I look at it as the hydrogens are on this carbon, the hydrogens on this carbon, the oxygens on that carbon, and then the carbons are together. So it kind of gives it to you in chunks. And so the way this is trying to tell you to do it is you're going to do a carbon with 3 hydrogens around it, attached to another carbon, and it has a hydrogen and it has an oxygen. We need to count out the number of valence electrons from the formula so that we know how many electrons to put into the structure. Carbon has 4, each hydrogen has 1, which means a total of 3 for those hydrogens, and then another carbon and a hydrogen, and oxygen has 6, that's a total of 18. And I'm going to start out by making single bonds. We always start off with single bonds, work up to double bonds if we don't have enough electrons to go around. When I do that, I've used 2, 4, 6, 8, 10, 12 electrons, and I still have 6 more to put in there. I'm looking for things that need an octet. This oxygen doesn't have an octet yet, so I'm going to put 6 around it. Now I've used all 18 electrons, and I can see that I am missing some, because that carbon there does not have an octet. So the way that I do, or kind of fix that, is I'm going to move electrons from something that does have an octet and has lone pairs into that double bond there. And when I do that, give myself a little bit of space here, now I have 4 electrons between them, and this oxygen still has its 2 lone pairs. When I check everything has an octet except for hydrogens, which are okay just having their duet. I cleaned up my Lewis structure a little bit to make it easier for us later. The next step is to predict the electron group geometry around the inside atoms, so those central atoms there. I'm going to have to do that for this carbon and also this carbon. Those are our 2 central atoms, and I'm going to label them carbon 1 and carbon 2. Carbon 1 has 1, 2, 3, 4 electron groups around the central atom. So 3 electron, 4 electron groups around the central atom. That gives me the tetrahedral shape for electron geometry. Carbon 2 has 1, 2, 3 groups. For electron geometry, that is trigonal planar. Our next step is to determine the hybridization of the interior atoms, those that carbon 1 and carbon 2. And again, I'm going to use the number of electron groups around them to decide that. So carbon 1 has 1, 2, 3, 4. So it has 4 electron groups or electron domains, and that means that it is sp3 hybridization. Carbon 2 has 1, 2, 3 electron groups or electron domains, and that means that it is sp2 hybridization. So I'm going to use that sp2 hybridization to draw around the central atoms. Okay. Here I'm just kind of summing up our last 2 steps. I said that carbon 1 was tetrahedral and it has sp3 orbitals around it. Carbon 2 is trigonal planar and it has sp2 orbitals around it. Now the challenge with this problem is we need to get a tetrahedral shape attached to a trigonal planar shape. So there isn't one shape there. It's a tetrahedral that's overlapping with a trigonal planar. And I need a little bit more room to make this happen, so I'm going to go to a blank screen. So here we go. I just kind of sum this up. So carbon 1 is going to be tetrahedral and sp3 orbitals. Carbon 2 is going to be trigonal planar and sp2. So I'm going to draw these out. Forgive my not great art. I will show you the pretty picture at the end. And I'm going to start by doing carbon 1 first. I'm going to draw the sp3 orbitals in a tetrahedral shape. This is one of the sp3 orbitals. This is another sp3 orbital. This is another sp3 orbital. And that's the last sp3 orbital. So I'm trying to draw them kind of how I do in a wedge and dotted line shape. The next thing that I'm going to do is that I'm going to draw my carbon 2 in a trigonal planar shape. The sp2 orbitals, and I need it to overlap with one of my carbon 1's hybridized orbitals, or otherwise we're not going to get a sigma bond there. So what I'm going to do is I'm going to use my green orbital, and I'm going to draw carbon 2 here, and I'm going to put the trigonal planar sp2 orbitals around it. I'm going to draw them in different colors, just like I did the first time. So this is one of the sp2 orbitals. This is another one of the sp2 orbitals. And this is the last one of the sp2 orbitals. And I just want to show that I am trying to make them in kind of a trigonal planar shape there as much as possible. We have successfully sketched the hybridized orbitals around the central atom. Now we're going to sketch the atomic orbitals on the terminal atoms in the molecule. And to do that, I just want to remind us what our Lewis dot structure looked like. It looked like this. And so we need to explain these bonds by doing an overlap of atomic orbitals. So we're going to try and explain all these hydrogen bonds and this oxygen bond around the outside. To do that, we need to look at where those atoms are on the periodic table. Hydrogens are in the s block, so they are going to overlap with their s orbitals. And so when I draw my hydrogens, I'm drawing spherical s orbitals around them. And on carbon 2, I need to pick, am I going to put the hydrogen here, or am I going to pick here? It doesn't really matter. I know that I'm going to have to put the oxygen somewhere, so I'm going to try and kind of leave a lot of room for the oxygen. So I'm going to put my hydrogen down here just so that I have plenty of room. Now I'm going to do my carbon to oxygen bond here. So I need my oxygen out here. And oxygens are in the p block, so they are going to bond with their p electrons, and I'm going to draw a p orbital around my oxygen. Remember, p's have 2 lobes, so I need to draw both lobes in there. And I'm going to put some electrons in there. Okay, so now I've gotten the single bond part, but I have not explained all the bonds. I have done most of them, so I've done this part, but if a pi bond is needed, which I do have a pi bond, every time we have a double bond, the first part is a sigma, which I've got here, but the second part is a pi bond, and that's the part that I need to do next. And so I'm going to do my, kind of change this up a little bit. I need to draw a pi bond, and a pi bond is made from unhybridized p orbitals. So I need to draw an unhybridized p around the carbon 2 and an unhybridized p around the oxygen. I think, let's see, I'm going to do it in purple because that's a color I haven't used yet. All right, an unhybridized p orbital looks like this, and there's no really great way of drawing these things so that they overlap the best. It's going to get messy no matter how I do it. That's why labeling our last step is so important, because no matter how messy your drawing is, a label can go pretty far to show what you're trying to say. Okay, so this is my pi bond here, and I know that it's going to obscure my carbon hydrogen bond there a little bit, but I'll label it when I'm done to make sure. Now I have explained my pi bonds, and the last thing is I need to label the bonds. So I'm going to label this one, and this one all the same. When we label them, we say what type of bond. They are sigma bonds, which are single bonds made from carbons sp3 hybridized orbital overlapping with hydrogens s, each individual one there. Then this one is also a single bond, a sigma bond, made from carbon 1's sp3 hybridized orbital and carbon 2's sp2 hybridized orbital. And I put the 1's and the 2's there because they have different hybridization, and I'm trying to be specific. I'm kind of going back to how I labeled this one here. I should have probably put carbon 1, so carbon 1's sp3. I should have fixed that up a little bit. Okay, so I'm just going to put that there. All right, so I have most of my bonds done. All right, this one, this purple one here, is a pi bond made from carbons, unhybridized p, and oxygens, p. This bond is a sigma bond made from carbons sp, so it's carbon 2's sp2, overlapping with hydrogens s. And then this bond in here is a sigma bond made from carbon 2's sp2, overlapping with oxygens p. And again, I want to remind you to use your Lewis dot structure so that to make sure that you have all the bonds that you need. And I'm just going to write our Lewis dot structure again up here to make sure that we have everything. So it's this. Okay. All right, so we have labeled these 3 bonds right here. We labeled this bond right here. We labeled this bond right here. We labeled this bond right here. And we labeled this bond right here. So I feel like we have explained all the bonds. That's what we need to make a good valence bond structure, or a good valence bond diagram. Okay, so we have gone, here's kind of the pretty picture. Here's our Lewis dot diagram. Here is our valence bond. So this is our valence bond diagram, or valence bond scheme. And yeah, maybe the picture is a little prettier, but I actually think that our work was a little bit better, because if you notice, like in this bond here, which is between the two carbons, which we labeled carbon 1 and carbon 2, they have not said carbon 1 and carbon 2. I think I would actually correct that. I think that they should have those there, because the carbons are different and they have different hybridizations, and so I want to say which hybridization is on which carbon. So there you have it. That's how we go from Lewis dot diagrams, or Lewis structures, to valence bond schemes, or valence bond diagrams. Remember, practice makes perfect.